Good day, everybody. So today let's take a look at certain reactions, and more specifically, those ones will pertain to the chemistry of aldehydes, ketones, and carboxylic acids to top things off. All right, so right now let's just delve into the reactions, and then we'll take a look at problem number one, right? So, and then the problem number one will look like this. So imagine we are going to have to deal with a compound like that, right? So it will have this kind of like cyclic alkane part to that, right? So then it will contain COH group, so which you need to recognize as an aldehyde group, right? So this is some sort of like cyclic aldehyde, right? So now let's imagine that we are adding two molecules of, guess what, an alcohol, CH3OH, right? So, and then we're going to carry out this reaction in acidic conditions, which are signified with H plus item here, right? So what are we going to do, right? So like once we react, see here, so like once we react the aldehyde with the two molecules of a certain alcohol, we are going to remember, right? So what are we going to make? So this is a common pattern, basically, that we are going to recognize that is represented by like two different, like specific unique aldehydes and alcohols, right? So, anyway, so once an aldehyde generally reacts with the two molecules of an alcohol of some sort, we are going to make not hemiacetal, but acetal, right? So, and then for our intents purposes, what kind of like we have been trying to instill in our minds is that those two alcohols total will lose two hydrogens, right? Which we can show this way. And then the aldehyde will lose the oxygen. So why is it important? Because it helps us to kind of like think about the side product that will be released, which is going to be HHO. What is that? It is H2O. So water will be released, right? We can just show it as minus H2O. So that's going to be the loss of water, right? So, and then the leftover parts will be connected, namely CH3O, right? With a free electron, essentially. That's can like make a bond, right? So because we will indeed make a bond between this carbon and this oxygen, right? So by virtue of the carbon having those two available electrons, right? Of course, just a regular disclaimer. So things mechanistically, in reality, happen in a little bit more difficult, more complicated way. So, but here we just like want to like see what's broken, what's made, right? So it's pretty straightforward. So like break, make. So that's it. So because we're on the intro level, so to say, right? And then yeah, so either way, no matter how we think about it, so like the point is to get to the right product, and then we indeed will get our product, which will look like this, right? So here note that we will have the central carbon, right? So which used to belong to the carbonyl group. So but now it contains this kind of like cyclic alkane part. It will still have the H, right? And it will use those like leftover electrons to connect to two methoxy groups, right? Or oxygen methyl OCH3, and you make a bond, and another OCH3, right? Because we have two alcohols. That's it. That's going to be your acetal. Acetal. If you want to recognize the acetal, so like there was a question about that, right? I remember. So some people are asking. So anyway, so here you can do that, right? So how do you recognize an acetal, right? So look for the pattern again, right? So you need to pinpoint kind of the central carbon, right? So which must have connection to an H, right? So in any acetal, there is going to be CH bond, right? So like present at this kind of like specific central carbon, right? Which is also connected to some sort of carbon-containing group. So it's going to be like a one group, right? So that's some sort of like carbon-containing group. It could be like cyclic alkane. Maybe it's going to be some kind of like long chain, maybe like butyl, right? N-butyl, for instance. Maybe it's going to be N-pentyl, maybe isopropyl in the second circle, whatever, right? So, but something with a carbon, right? Typically, that is contained to the central carbon. And then the central carbon also must contain the connections to two O something group, right? So here we have oxygen. Oxygen will be present in like any acetal in this these positions, right? So, and then in turn, this oxygen will be connected to some sort of alkyl group typically, right? So because we are introducing those two circles basically from alcohols, right? So H is removed and then the leftover parts are introduced. So that's what you need to look for when you're looking for an acetal, right? So CH bond is pretty much like set in stone, right? And then this can be some kind of like alkyl group. This is oxygen with an alkyl, oxygen with an alkyl. So that's what you need to look for in acetals. In ketols, the only difference will be this H, right? So instead of this H, you are going to have connection to some sort of carbon containing group. So some kind of a carbon chain typically, right? So based on our experience so far, maybe instead of like H, for example, you have methyl, ethyl, propyl, isopropyl, whatever, right? And if you have exact same molecule, but you switch H to some sort of like methyl, for example, or ethyl, then you're going to have a ketol. So that's the key difference. Pay attention to this like H and CH bond, right? Particularly in this sort of central carbon, so to say, right? That contains the features that make the molecule an acetal, right? Or a ketol. So anyway, so now let's move on to problem number 2. So here we go ahead and then take a look at the reverse formation. So P2, hydrolysis. So what is that? So here we recognize H, CH3, OCH3, just like we talked about now. So this is an acetal, right? So acetal. Acetal was formed by virtue of one aldehyde and two alcoholic molecules reacting with one another, right? So these ones, as we saw, came from an alcohol. So O methyl or O with some sort of like alkyl chain, O with some sort of alkyl chain come from an alcohol, right? So hydrolysis basically will need to deconstruct, right? So those things, or this big molecule into like two separate molecule types. So it is going to be like in H plus and then H2O, right? So H2O will be applied in acidic conditions, right? So that's going to be hydrolysis. And then we're going to make two molecules of alcohol, which is going to be 2CH3OH, right? So just remove this and remove that. They are identical. And then we make two alcoholic molecules, just like this, right? So now leftover part, CH3CH will need to be turned into an aldehyde, right? So because we almost have an aldehyde, CH, and then something's missing. What's missing? Let's figure it out. CH3, CH, right? What do we need to do to make this into an aldehyde? Well, that's it. You just need to make a carbonyl group, right? So that's your like starting materials basically, so that were used to make this product. So, but now we go in reverse, and then the product becomes a reactant, which undergoes hydrolysis in acidic conditions to make the products, which could be also used as reactants, dependent on what side they are, right? So here you have the hydrolysis, which gives you the aldehyde and the two molecules of alcohol, 1, 2, 1, 2. And then 1, 1, right? So into the aldehyde it turns. All right, so and now let's take a look at some more examples. So it's going to be like problem number 3. Another hydrolysis event, so which is going to be looking like this. A little bit different this time around. Let's imagine we have a structure like this one. Cyclic triangular shaped alkane piece. So here we have it, right? So that looks like O with some group, O with some alkyl group. We have the central carbon here, right? That has connections to like O alkyl or alkyl. And then it has connections to not H, but two carbon-containing groups. So what is that? It is a ketal. So if you look at this part here, so that will be resembling the ketone. It almost looks like a ketone, except it misses something, right? So guess what? And then these parts resemble the alcohol, which was used to make this molecule. But now it undergoes the reverse reaction, basically, which is going to be called the hydrolysis, acidic conditions with water, right? So which needs to be used for hydrolysis. Now we're going to, again, break this bond and that bond. And then we're going to turn this piece into the ketone. And these two pieces will be turned into the two molecules of alcohol. Just NH. That's it. That's your two molecules of alcohol. And this part needs to be turned into a ketone. How? We need a carbonyl. So now it is a ketone, right? So that's it. That's going to be your ketone. That's going to be your two molecules of the alcohol. So hydrolysis was performed on this particular ketal. So that was a ketal because we can identify the ketal since we have this carbon that's connected to O carbon group, O alkyl group, another carbon group, and another carbon group. So that's it. So that's what you're looking for, to make it not an, to identify that molecule not as an acetal, but as a ketal. So, and then we make, from the ketal, we make ketone upon hydrolysis, right? Alongside two alcohol. All right. Now, we kind of like jump back and forth here a little bit. P4. What are we looking at right now? So we are looking at the following molecule. We're looking now at the ketone. It's going to be an aromatic ketone. So just to switch things up a little bit. Two phenyl groups. This is a phenyl group. So now imagine that we're going to add two molecules of isopropanol. In acidic conditions, what are we going to get, right? So that's the question. So we're going to make a ketal, right? So because we have the ketone reacting with two molecules of an alcohol, isopropanol in this case, right? So we're going to chip away two H's and oxygen. This will give us like minus H2O, right? H2O will be released. And then we're going to make our final product, which will look like this. Okay, so we are adding this part, basically isopropyl O. That's it. That's your final ketal molecule right there. Ketal is formed, right? So, great. Now let's take a look at some more problems, right? So we're going to move on to a chain of reactions. So to just take a look at several types of reactions, several steps that will lead us to the final product. Okay, so I'm going to remove everything, and it's problem number 5, looks like. So let's imagine we're going to have an alcohol like this. It's just a good old 1-propanol, right? So somehow we're going to receive this molecule after several steps, maybe 1, 2, 3, whatever, right? So we need to like think about it. We're going to receive a molecule like that. CH3, CH2, CH. Ethyl. Think about what ethyl is, and then you'll be fine. All right, so you'll be able to know what this ET stands for. It's ethyl, right? So you can redraw it. It's good for your practice, by the way, right? To connect particular, to connect particular terms to the structures. All right, so what happened here? So this molecule looks like we have carbon here with H, O-ethyl, O-ethyl, and another carbon-containing group, right? So what is that? This is going to be our acetal, right? We're going to make the acetal. Acetal is produced from an aldehyde. So this is going to be our aldehydic part here, CH3, CH2, CH with an O as a carbonyl, right? In the carbonyl group, we'll make the aldehyde. So these came from two alcohols, right? So two molecules of the ethanol, by the way. So we're going to like make basically this molecule from two molecules of ethanol and one molecule of propanol, right? So one molecule of propanol. By the way, when I say that, like propanol, right, for example, then you need to try to put this like words into, or this word into the structure, right? So it's just the third or like whatever. So it's like one of the kind of like simpler aldehydes, right? So it was just three carbons in the chain. All right, so this is our one propanol, right? So one propanol can be turned into aldehydes, right? Because in general, alcohols, primary alcohols especially, can be turned into aldehydes. How? By oxidation, right? So let's go ahead and try to oxidize this, right? So we're going to apply oxidation. Is going to be mild oxidizing agent, MOA. And then we're going to do the oxidation, right? So basically, in this case, we're going to make an aldehyde, which will correspond to the oxidation process, because we're going to decrease the number of hydrogens in the molecule. And that's what we're going to get. So basically, you will kind of like recombine the OH part, and then you will remove two H's, right? So, and then you make your aldehyde. So this is going to be nothing more than propanol, right? So propanol will be made. So that's like 1, 2, 3, 3 carbons. That the root will be propan, right? And since we have the aldehyde, so we have propanol. So propanol. So propanol will be produced. So then next step will be just, okay, this is our propanol kind of like backbone, so to say. That's the one right here, right? So you can see this resemblance. All right. So we are going to have to apply the second step, right? Which is going to be the application of two molecules of ethanol in acidic conditions. So we're going to remove two H's and one oxygen, right? So like H2O will be released. And then if we look at this, we're going to make this very molecule, by the way, right? So that's it. We are at the final stage here. So yeah, that's all. So yeah, basically two electrons can be now making bonds with two O-ethyl groups. All right, so that's it. And then, yeah, basically you'll remove oxygens, you will attach two O-ethyl groups, and then you will make your final product. That's it, right? So again, all the familiar reactions. So you can start thinking like from the backwards, basically from the final product. Okay, how is the final product made, right? What was the penultimate product, and so on, until you kind of like figure out how you arrive at the initial product, and then you just need to show the like synthesis steps, which will lead legitimately to the final product, right? So that's ultimately because ultimately we're moving in the forward direction, right? We start with some reactants, and then we continue making products several steps down the line, right? So, but for our thinking purposes, we can kind of like think back, right? So, but we need to show the like forward reactions, basically, from the initial product to something more complicated, typically. All right, so that is problem number 5. Now we're going to switch gears and we're going to take a look at the carboxylic acids briefly, right? Which is kind of a follow-up to aldehydes, essentially. Like it is something that can be built from aldehydes, or synthesized rather. So let's take a look at the like acid, right? So some acid, which is going to be looking like this. So we have quite a bit, quite a bunch of carbons. 1, 2, 3, 1, 2, 3, 8 carbons. All right, so pretty good. Bear with me. We're going to draw that. All right. And then all right, so what do we call it, right? So let's think about it. So typically carboxylic acids will have the suffix oic, right? So it's going to be some kind of like propanoic, butanoic acid, for example, right? So here we have a much longer chain, right? So that's going to be our longest chain, looks like. So it will contain 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons, right? So 8 carbons in the chain. So it's going to be some sort of like oic acid, acid. What's before oic, right? So that's going to be the root that corresponds to the alkane, basically, that contains 8 carbons in the chain. So we have hexane, 6, heptane, 7, octane, right? So we'll use the root octane, oic acid. So that's it. So that's our name, right? So before the substituents were introduced. So it will be just octanoic acid. But we have here this guy, right, which is going to be phenyl, PHENYL, phenyl. Phenyl group is on carbon, right? Number something. So how do we count it, right? So we're going to minimize the number for the carbon that contains the carbonyl or carboxylic acid group, right? So that's going to be not like here, huge number, 1, 2, 3, 4, 5, 6, 8. It's not 8. So it should be counted right to left to minimize the numbers for the number for this carbon with the carbonyl group of the carboxylic acid. And then if you count right to left, we're going to assign this guy number 1, right? So 1, 2, 3, 4, right? So 4, 5, 6, 7, 8. So yeah, it is indeed the octanoic acid, except at carbon number 4, we have the phenyl. So consequently, let's show it this way. We have 4-phenyl, 4-phenyl, 4-phenyl octanoic acid, right? So this is going to be our thing here. So now let's take a look at the Lewis structure. And that's going to be the next step. So we just want to add lone pairs to the oxygens, right? And then you will see it pretty much in like any carboxylic acid. A very good pattern to have. So that's our lone pairs on the oxygen, and that's it, right? So now let's show how some sort of carboxylic acid will dissociate, right? It's an important part, maybe like one of the like foundational chemical reactions of the acid. It's their dissociation, right? Before we start reacting, excuse me, before we start reacting them with anything else. So let's show some sort of like other acid, maybe something more friendly in terms of writing. So let's maybe show an acid which will look like this. So we have phenyl group, and then we have so that's going to be our acid, right? No need to name it now, but we are going to show its dissociation, right? Acids are proton donors, right? So the CH bonds do contain H's, right? So, but they're very unreactive, right? So CH bonds. So consequently, we are going to find other bond that can potentially donate the proton. That's going to be this bond, OH, right? So just like in water, remember, HOH, the OH bond will dissociate. Same here. So we do have the OH bond. So like, why not to dissociate this one? And indeed, that turns out to be reality, right? So we have this bond that will dissociate. Both electrons in this bond, so which we'll try to show with the dots, will go towards oxygen because it's more electronegative. Lone pairs, by the way. So now let's show the dissociation result. So this stays, those like 3 CH2 pieces in a row. Then we'll have CO with lone pairs, right? So then next, we have this oxygen with 2 lone pairs. But then, maybe let me switch colors a little bit, red, right? So we have here a red electron and another red electron that will represent the OH bond. So now both of them moved to oxygen, right? So because H kind of like lost its electron. So like one electron was lost by H, and then essentially this entire pair consequently, right? One electron from H is added to one electron from oxygen. So the entire pair is now on oxygen, right? So let's show it this way. That's from oxygen and that's from H. Consequently, so we're going to have the charge on the oxygen. So it used to be neutral atom, but now we're going to have a charge of -1 on the oxygen because it gained an extra electron. 0 and -1 becomes -1. All right, so that's the charge on the oxygen minus. And then it's going to be the case in like pretty much any carboxylic acid that you can be asked to dissociate. Another thing that will be formed will be the proton, right? So because that's what acids do, plus H. So H here used to be neutral atom, but it lost one electron. So it went from 0 charge to +1, right? So -1 becomes +1. 0 minus -1 becomes +1. Or if you want to think about that in terms of like charge balance, right? So you used to have a neutral species of H atom, which lost one negative charge. Consequently, it needs to be +1 charge generated, right? So one negative out, one positive in, right? So that's why you're going to have H plus, or you might as well remember that, or you should know that acids do produce H plus, right? So that's one of the products. So that's your H plus ion proton, so like donated by acids, and that's your like unique counter ion that's dependent on the structure of the acid. So that's it. So that's your acid dissociation right there. And at this point, we are done. So yeah, thank you for your attention. Stay focused and bye everyone.